Hello and welcome to another orbital mechanics video. Still going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition. I'm up to problem 3.8 and I'm going to do 3.9 as well in this video. So 3.8 states a satellite is in Earth orbit for which the perigee altitude is 200 kilometers and the apogee altitude is 600 kilometers. Find the time interval during which the satellite remains above an altitude of 400 kilometers. So if you imagine this is our orbit, we're going to be going up to roughly B, then we're going to be above 400 kilometers until we go back down to 400 kilometers on the other side of this ellipse. So to do that, we can first get our eccentricity, which is radius apogee minus radius perigee divided by radius perigee plus radius apogee, and then we can get the semi-major axis as well by the radius apogee plus radius perigee divided by 2. And then we have the radius at which we're looking to be above, and then we can also get the angular momentum using the this equation here rearranged, and then we can get theta at which point, at the point that we're actually hitting 400. That's the orbital formula. And then we can get E using this equation that we've been over in previous videos, and we can get ME after that. We can get the period because we know that we're going around Earth and we have the angular velocity, so we can use the period equation to get the period, and then T1, the point at which we hit 400 kilometers altitude, is here, and then to get the time that we're above that 400, which is going to take the total period minus the time up to 400, which will be twice because it'll be happening on both sides. So if you look at this diagram here, it'll be up here, it'll also be down here, and we're going to cut off all that bit that is below 400. And that's it for 3.8, pretty straightforward. And 3.9, an Earth orbiting satellite has a perigee radius of 7,000 kilometers and an apogee radius of 10,000 kilometers. What true anomaly theta is swept out between t is 0.5 hours and t 1.5 hours after perigee passage, and b, what area is swept out by the position vector during that time interval? So to do this one, we're going to have to use a numerical method to get the answer. We have the gravitational constant, we have radius perigee, radius apogee. We can get the eccentricity from those, and the semi-major axis and the angular velocity. We can also get the period, and we're given the time in hours to convert those to seconds. And then to get the angle, we've got a function here defined where we have the mean anomaly we can get from the period and the time that we've been given, and then we can solve for E, the eccentric anomaly, using our Newton method. If you go back to, I think, problem 3.2, I go over these, and you can get the Newton method code from there. So solving that numerically, we get E, and then we can put that into our tan equation for theta, and that's our theta, and we do that twice, once for T1 and once for T2, and then because it's using tan, we end up with a net on the other side of after the apogee, we're getting a negative value for tan, but we can just flip that around to add on 360 degrees to give us a positive value, and then subtract theta 1, so that's theta 2 minus theta 1, and then to convert to degrees, and that gives us the answer. So if I just run that, you'll see we have 128.7, which is the same, and then for the area formula is the change in area over the change in time equals the angular velocity divided by 2. So we can integrate that and we get the area, just multiply h2 by the time difference, and we get 1.03 by 10 to the 8 kilometers squared. So yeah, that's that. You should be able to steal that and copy it out if you want. If you think I've made a mistake or you have any questions, leave them in the comments. Thank you very much. Goodbye.